Friends and colleagues, welcome to the Cosumnes Subbasin groundwater classroom. We're going to spend about 2 hours. It's 1 o'clock right now, right? We're going to go till about 3. I'd like to introduce John Fio, groundwater modeler extraordinaire, all-around good guy. Any other words of intro? You want to just jump in? Do we want to go around the room and do introductions, or do you want to pretend that you're university students and maintain your anonymity?
I like the second option.
Second option, okay, very good. All right, welcome, enjoy.
All right, well, you know, it's a big topic, and you know, there's some tension in trying not to rely on things like technical jargon, you know, and so forth, and at the same time trying to give information that's, you know, available and meaningful to a broad based audience. So I hope we succeeded on this. This you know, based on the you know, some of the preliminary stuff that like Tom's interviews and you know, various conversations and so forth. This is basically the outline of the topics that we came up with to talk about this afternoon. One of them, just to very briefly talk about, you know, why model, you know, why are we doing this in the first place. Then some like basic concepts to deal with groundwater flow, because that's basically what a model is doing. It's simulating groundwater flow. And then talk a little bit about the types of data that go into a model. You know, all models require data. Talk a little bit about the adaptability of a model once you have one for the future and maintenance and so forth. And then to talk a little bit about the you know, available models and applications, you know, for this basin, for the Cosumnes Subbasin. So first off, you know, it'd be good to talk about what you know, what models can and can't do, because for a lot of people they're just a black box, and they can also be a source of great suspicion. And basically, you know, models are a way, you know, they're used to quantify groundwater conditions. Okay, and that's a concept that, you know, is important for us to get across. Is that, you know, the real power in the room is this. It's still this. It's what's in here. But a model is a way to take from what's in here and to put it down and to quantify it in a very unbiased way. So if you have a mistake up here, your model won't work. Okay, no matter what you try to do to it. But it also helps you keep honest, because a lot of times people can be developing a model or running it, and it doesn't give you the answer they want, and so they begin to think it's wrong. And usually it's not that the model's wrong, it's usually the person that's building it that's wrong. But specifically, you know, what the model does is it quantifies water levels, you know, the level of the water in the aquifers beneath land surface. And because it quantifies the water levels, it also gives us information on the direction of groundwater flow and the rate of that flow. And then finally, with that information, it also tells us what's going on in terms of how much water is stored and what the changes in that storage is. And so you can begin to see that you know, they're very useful, because they can not only can they help you understand what's going on now, but they can also help you understand what's going on in the future, at least to make best guess projections of the future. And you know, finally, an important point is that, you know, the model just gives you quantitative information, and it's that information that you use to make decisions. You know, the model doesn't make decisions for you. You know, there are methods in modeling that can help you identify what the best solution might be under a certain set of constraints. But ultimately, it always comes down to the person who is getting the information. They're the decision maker. The model is just a tool. Why is a model used or needed for this process, for the groundwater sustainability plan? Well, specifically, we're required to develop quantitative information on current conditions, and we're also required, as part of our planning process, to be able to project what the conditions will be 50 years into the future. And that projection can be based on things that aren't in our control, like climate change. Or it can be things like projects that any entity wants to develop as a means to develop a more reliable water supply and to look at the effectiveness of the projects over time. Specifically, we are asked to develop not only information currently, but projected on what they call the cones of depression, and that's where if you have a lot of pumping and you're dewatering the aquifer, you get what looks like an inverted ice cream cone. Or it can be over a much larger area where you have a number of wells pumping, and they're all making their own little ice cream cones, and the open part of the cone starts growing, and then they start connecting, and so it gets even bigger. So it's always additive. Everybody that in a groundwater system, anybody who's taken out water, it all becomes additive with everybody else. Nobody is an island to himself. It also, it's important in terms of the depth of water because it can affect things like the pumping lifts. The depth of water can also affect whether or not your well, which is basically fixed in space, whether the water level falls beneath the screen in the well, and so forth. We're also required to develop that same information on current and projected future conditions, what we call a water budget, which is a compilation of inflows and outflows. Just like a bank account, you have your income coming in and your bills going out, and the balance of your checkbook is what you have in storage. And we're required to calculate that for the resource that's beneath the ground and that we can't see. And so that's why you need a model. And then it's also to help us, with these projections, like I said, to select different projects that are meant to either remove or prevent against undesirable results. And then finally, one of the useful things about models is that they help you to develop effective ways to monitor the basin. And what you want to do is you want to monitor it not only to measure the effectiveness of any plans that you've developed, but it's also to monitor it in a way that if there's one of the real useful outcomes of models is that it helps you understand what you don't know. Like I was saying earlier, where the things, if what you think and what your model is telling you aren't agreeing, then it's a good sign that there's something you don't understand, and so it helps you identify what kind of information you need to collect in order to bridge that gap, to remove that uncertainty. And so I have a little video here that that Kat and the Water Forum helped me splice together, but it's an introductory video on just the basics of groundwater flow.
Aquifers are rarely underground lakes like you might see in a cave. They are typically rock formations that are mostly solid, but like sponges, they have interconnected fissures and pore spaces that hold water and allow it to move within the formation. An aquifer is best defined as a layer of saturated rock and the water in its pores. Aquifers are formed very slowly over vast periods of time. Water in aquifers comes originally from the surface of the earth. When rain falls, some of the water infiltrates underground and collects in the pore spaces. Water in rivers and lakes can also seep into the subsurface pores. Eventually, some interconnected pore spaces become saturated with water. In other words, they become an aquifer.
The ability of an aquifer to produce water depends on the properties of the aquifer's rock formation. The two most important properties are porosity and permeability. The porosity is a measure of the volume of empty space, or pore spaces, inside the rock. Pore spaces can be openings between grains, fractures in the rock, and even caverns. Porosity represents the volume of water a rock formation can hold. Porosity itself isn't enough to create an aquifer. The areas filled with water must connect with each other so the water can flow from one pore space to another. That connectivity between pores is known as permeability. Permeability is a measure of how readily water can flow within the rock. Rocks such as pumice and shale can have high porosity, but do not form productive aquifers because the pores within the rock are not connected. The permeability of pumice and shale is low. On the other hand, gravel transmits water quickly because of large connected pore spaces. The permeability of gravel is high.
Compared to water movement through rivers or lakes, the rate of movement through an aquifer is slow.
Managing groundwater is the same as managing any budget. A household cannot continuously spend more money than it earns. In the same way, an aquifer cannot continuously give more water than it is taking in.
Accounting for the groundwater budget requires thinking about the water cycle. The water cycle is the continuous movement of water on, above, and below the surface of the earth. Water that enters an aquifer from the surface is called recharge. Recharge includes rainwater that seeps down through the soil to reach the water table. Only a small portion of total precipitation gets down this far. Recharge also includes water draining into the aquifer from streams and lakes. Water that enters from another aquifer is called inflow. Inflows and recharge are comparable to a deposit in a bank account. They add to the overall wealth of an aquifer. Water exiting an aquifer naturally or artificially is called discharge. Examples of naturally occurring discharge are evaporation, groundwater used by plants, springs, leakage into streams or lakes, and leakage from one aquifer to another. The most common discharge from an aquifer by humans is pumping. Discharge is comparable to a withdrawal from a bank account. The amount of water inside an aquifer is called storage. This is comparable to a balance in a bank account. Anytime we pump water from an aquifer, we are drawing down the water level in the aquifer storage. As long as the amount of inflows can replace what we pump, drawdown is temporary and does not affect water availability. When inflows can't keep up with pumping, we are depleting the aquifer. Prolonged pumping in excess of inflows reduces the amount of water in the aquifer, and as a result, pumping becomes more difficult and costly, as water must be lifted from increasing depths.
Okay, so that's some of the basics, just behind groundwater flow and groundwater systems. And one of the things I wanted to talk about first is this whole thing. Sometimes you'll hear them talk about an HCM or a hydrogeological conceptual model, and all that is it's the understanding that we have up here of what's going on out there. And so if you can think of this as being sort of like the Cosumnes Subbasin, you have all kinds of things that are going on. First, you have a structure of of what your groundwater basin is like, and what I'm talking about is the aquifers. And so, like in this diagram, it's showing that it's not just one big homogeneous or uniform piece of material. There's variability. There's clay beds that don't transmit a lot of water. But they can impede the movement of water between two different water-bearing zones. You also have things that are going on in terms of on the land surface that have an incredible amount of effect on what's going on beneath it in terms of the water use and the water that gets back into the system. You can have surface water, groundwater interactions that occur along creeks and streams and so forth. You have wells that can be pumping from variable depths in different water-bearing zones. And then just the variety of land uses and the amount of activities that go on that consume the groundwater. Because one of the things that is important to recognize is that a lot of times people talk about pumping, but what's most important is how much of that pumping is consumed, right? Because that's the part that doesn't get back in. Sometimes there's pumping that goes on that is like a short circuit that takes the water out, but it goes back in. Okay, so that's an important component to understand. But anyway, the real point of it is that when you start to break down the groundwater basin that you're interested in, there's a lot going on. you know, and it's a lot to account for. And so you really have to have a very structured way of doing that. You can account for a lot of these processes and make calculations and so forth. You can do it on a piece of paper. It takes a lot of time and a lot of effort, but you can do it. And you know, they used to do it all the time. Now with computers and some other technologies, you know, you can do things faster and a lot more effectively, and as well as it gives you a lot more power in terms of dealing with projections. But ultimately, you know, what your groundwater flow model is designed to do is to take that concept and to put it in a computer so that you can make these calculations to quantify your concept. One of those concepts is that, you know, it's an aquifer. You can kind of think of it like a sponge. It's not a perfect analogy, but it does have a lot of similarities in that it stores water. You know, we all are familiar with a sponge. If you if you put it in a bowl of water and you let it absorb to its full capacity, you know, you can pull it up and it'll be draining under gravity. And you know, that's just like in an aquifer with a water table. You know, it can be draining under gravity if there's a place that the water can go to. And then you get to a point where it doesn't drain anymore, but that doesn't mean it's devoid of water. You can squeeze it and get more water out of it. And unfortunately, when that happens in basins that have what they call unconsolidated sediments, meaning that they're like sand, silts, clays, and so forth, and under certain other conditions, you can actually have a situation where by lowering the water levels, the burden from the overlying soils and everything that's on the land surface starts to compress those fine-grained clays just like a sponge, and it'll squeeze water out, a lot of water. But unfortunately, the land surface sinks, and that's what they call subsidence, and you can't get it to come back. Okay? And then finally, the other concept or the point that is important is that, and they did a good job of that in the video, is the relationship between porosity and permeability or hydraulic connectivity. You know, just because you have a material like a clay that can have a lot of water in it, it doesn't have the same connectivity. You know, the water it's much more difficult for the water to move along the various paths than the water that would be in like a gravel. Okay, so those are important. So even though you have something that can have a lot of water in it, it doesn't necessarily mean that the water is accessible. And then this is another slide just to emphasize that point, is that, you know, what we're really talking about in terms of groundwater movement, you know, we're talking about the amount of water that is actually in between the individual grains. You know, whatever those grains represent, whether it's boulders or sand or clay would be flatter, but you know, it's whatever is between those solids. It's the water that's within those pores, and then it's the movement of the water through the pores that results in groundwater flow. And those sediments, you know, especially just like this basin, they can be all different kinds of what they call texture. You know, you can have all the way here on the left, you can have what's clay, where you have very, very, very small sediments, and they're able to compact together really tightly, and their pores they have a lot of pores, but the pores are extremely small. And you can move up the scale from clays to silts to sands, and then finally to gravels, okay? And in a groundwater system, you know, these are the things that, if you're interested in getting water out of it, these are the things that you like to see. Those are your aquifers. These are the things that are difficult to get water out, and those become what they call like your confining beds or your aquicludes, or so forth. I just had another thought and it escaped me. But I guess I was going to make the point that in a real world aquifer system, you're going to have a mix of these things, and you'll have you'll have depth intervals that'll be primarily the coarse grain sands and silts. You'll have depth intervals that'll be primarily the clays and the sands and gravels, and you'll have depth intervals that'll be primarily the clays and silts. And then you can also have mixtures of these, like silty sands, clayey gravels, and so forth. And depending on the relative combinations of the different textures, that determines how good of an aquifer or how well it yields water. So we have this concept of sediments and sediment textures and how it relates to the ability of a formation to store and transmit water. There's also a concept of where we would expect to see these things. This is just a diagram that, you could think of this as like the Cosumnes River. But it's all about how these materials that start out in the mountains and rocks, and they're slowly broken down with time, and they're transported down to the valleys with surface water. And so as you move down the river, it's losing energy, and that's what this diagram is showing us up here. You have these high rushing streams and rivers and so forth, and as they get down to the valley, the energy starts to decrease, and as it starts to decrease, then the river starts meandering, until finally when you get down into like the very center of the valley, it can just pool out like in a marsh, okay? And everywhere along that route, you'll get a difference in terms of what kinds of sediments you expect to see. Up near the foothills and at the base of the mountains, you expect to see a lot of big coarse-grained things, boulders and coarse gravel and so forth. And as you move down, the materials that can be carried with the water, they have to get smaller in size. And so then you start seeing a fining of the sands, you start to begin to see the silts and the clays, and then finally, you may get down to the end down into a marsh or so forth, and it'll be primarily all fine-grained materials. One of the interesting things is, like in here, one of the complexities that you have in this basin is the fact that, it's defined, the basin boundaries are defined, but they're not defined by like physical barriers. It's not like it's a closed basin. And one of the interesting things that you see, like if you go into some of these like desert basins and so forth that are truly closed, they're basically a valley surrounded by mountains, and you'll see this kind of thing. Except, all down here, this is because there's no place for the groundwater to leave except where it gets really shallow and then it evaporates to the land surface. And then you'll see these, big playas. And the playas will be primarily fine-grained materials, really thick things of clay. And then they'll have salt crusts all over them from all the, eons of the water coming down and evaporating and leaving the salts behind. So even though it's complex, in terms of the geology, there are patterns that we can see and use to our advantage in terms of understanding and quantifying groundwater flow. This is just a continuation of the concept that I was talking about in terms of deposition of sediments, the depositing of the sediments. And what we're showing here is how over time, when you have these streams like meandering, they can also change courses. And you can see the patterns in here of the old stream channels. And then it's really important in terms of over time with depth, you can see that these were old stream channels at earlier points in time. But what happens is those stream channels, as the stream moves, and then they start getting the fine-grained deposits laid down beside them. So you get all these what they call buried stream channels. And in fact, you can see some of the properties in here where you can still see the green up here, which is probably indicative of the topography being a little bit lower and the water table being a little bit shallower, as opposed to the other areas that you may have higher topography and a deeper water table. But the real important thing is the real important message in all this is that in dealing with a basin like this, the term I always like to rely on is that they're called messy aquifers. Okay, there's just no rhyme or reason really. It's very difficult to quantify the channels of this channel here, this channel there, and this depth here, and this depth here. There's just too much going on. There are tools to try to reduce that uncertainty, but it's really difficult to map this out like you would a plumbing system. Okay, where you know where the pipes are, you know where the water's going. This is much more complex.
How would you characterize the Cosumnes Basin? Are we down into that meandery portion of the lower valley? Are we still?
You have almost all of it.
So we've got a messy aquifer.
Yeah. Yeah. In fact, here's a picture of what it might look like. But this figure here, or this photograph here, is nice because, like I was talking about what was going on spatially and over time. What it's showing here is you can see in a vertical direction, where here there were a lot of fine-grained clays, and so at this point in time you had whatever surface water feature was depositing the sediments. At this point, it was depositing the fine grain things, so it was slow moving.
Question, how many of these vertical slices or views would you need to put together a decent modeling replica of the valley of our basin?
Well, there is no magic number.
The
But-
more the better?
Yeah, but well, there's an economy of scale there. There are other things besides slices that you can do, and I'll talk a little bit about that as we get into it. But you definitely, I mean, that, Sigma requires that you have at least 2 of those slices in order to be compliant. Right now, for this basin, we're working on 4, which is trying to look at what's going on in both directions, north, south, east, west. But anyway. So the point here is that you get these fine grained materials, and then there was a more humid period of time, or where you actually had the stream channel or the stream water flowing through a stream bed, and so you got these nice sands and gravels. Then up here you get another fining where this is actually a mixture of gravels and clays, and then you get back up here and you have more fine grained clays. And so with depth you can see these variations. And so if you were out, drilling a hole and you wanted to put your well in, of course, this is where you'd want to have your screen because that's where you're going to get the water. And that's why when wells are drilled, the drillers are required to record the type of materials that they're going through as they're drilling the hole. And they make a record of them. And there's hundreds and hundreds and hundreds of those records now. And that's why it's really important for us to get our hands on them, because you can start looking at them at different locations and saying, okay, at this location we see this. At this location we see this. And then once you start seeing that, then you can start doing these vertical slices like you're talking about, or cross sections, and see how things are varying in different directions. And you start putting together an idea in your mind of how the groundwater system is structured. This map over here, this is kind of an interesting one. This was produced by DWR back in the early 70s. Where they were using those boreholes, the drilling boreholes. And what they were doing here is they were showing, they were trying to map those buried stream channels. And the Cosumnes River is right here. And, is it right? No. There are aspects of it that are probably right. But this is, there's interpretation involved, and they were limited in the data they had. There's more boreholes now and so forth. But it gets across the concept that you can have these buried stream channels, but they're not all connected. It's not like there's an underground river. I can't tell you, there have been several times in my life, people talking about the underground river that comes from the Sierras and it discharges at the Pacific Ocean. It's not like that. It's messy, like we were talking about earlier. It's messy. But most definitely, if you're standing here, there's a difference between what's going on here and what's going on here. But when you're looking at the whole basin, these things their effects start to mix. They start to contribute, to each other. So we've talked a little bit about, the structure of a groundwater basin and how this is a messy basin. And now I wanted to talk a little bit about, the movement of water through these sediments, because we talked about how these sediments might be structured. But now we want to talk about how water moves through it. And what we're showing here is just, it's very analogous to a concept of like water flowing through a canal, or a straight stream or something, where you have the concept of, you're going to have a velocity and you're going to have an area of flow, and that's going to tell you the quantity of flow. The quantity of your flow is the velocity times the area. Well, it's very similar in an aquifer system where here's a block of sand, and with like a canal, if it's it's being driven by gravity, the slope of the canal bottom, water flowing downhill. Well, it's the same thing in an aquifer in terms of it's the water flowing downhill, but it's based on the slope of either the water table or the slope of what they call the piezometric surface, which takes into account pressure. But at any rate, you have a force that is pushing the water, and then you have an area of flow, and so that gives you a velocity in an area, and that gives you a quantity. And this is how a groundwater person would write it. Flow is equal to this, which is, we'll talk about this in a minute, hydraulic conductivity, which is its ability to transmit the water. And then this is kind of like, the slope of land surface, or the slope of your canal. And they call this a gradient, but it's the difference between the water level between 2 points over the length. And so this is what is driving the flow. This is its ability to transmit the flow, and this is the area of the flow, and it gives you, the flow that you're after. And we're going to talk some more about this. In fact, I even have a video here that I don't know. It's kind of it might be nerdy, but I liked it because it just shows you that people really do measure this stuff, and then also I like it because you actually can see, because we can't see the water flowing underneath us. We can go out and see signs of it sometimes. We have a seepage face, along a road cut out or along the bank of a river, but we can't see it flowing through the soil. But you can actually see that, oh yeah, it does come through. It does come through a chunk of soil.
Well, in this test, we're going to determine the permeability of the soil, also known as hydraulic conductivity. And for that, we use some soil and the testing equipment. So when you assemble it, that will be the seal that you're relying on. So these wing nuts, there's 3 of them. Once I open the outlet in here and the inlet, now we have a water circuit that is coming from the inlet here, coming down. It's very important to get rid of all the air in the system. So steady state, we're causing flow to come into the sample from the bottom, flowing upwards. And now we're at a steady state kind of condition. So it's in equilibrium, and all is involved in measuring the hydraulic conductivity is 2 things. You have to measure the height difference between this outlet point and the top. So that will be the change in elevation from the top to the bottom of this 0 condition, because that one is level right there. So that's one number, and then the other number that we'll need to be measured is the flow rate, or the rate of flow, how much water is coming out of the system per unit of time.
Okay? So that gives you a little feel for when somebody talks about hydraulic conductivity, what they're talking about, not only in terms of how it's used in groundwater studies, but it also gives you a sense, a visual sense of what it is. And so, one of the things you'll hear when people are talking about groundwater, you'll hear almost as much as hydraulic conductivity is this thing called Darcys Law. And it's really one of the fundamental principles that is used in groundwater investigations. And this is very similar to that earlier figure that I was showing you. But remember, what we're after is the flow here. And this is that same formula that I was showing you, where you have the area of flow, and then you have the hydraulic conductivity, which we talked about, and then you have this gradient, which is the difference in the water levels over a certain length. And so this could be like two wells, within your groundwater basin. And those 2 wells, they're separated in space, and they're not necessarily experiencing the exact same things. There could be things going on that affect the water level here, and there could be things going on that affect the water level here. But it's the difference between the water levels at those 2 locations that is driving that flow through the aquifer. And so this is another reason why it's really important for managing a basin that you have points to take these measurements, because you can't see it. You can't see what's going on beneath you. So this is why people are really interested in who has wells and where they're located and where those wells are screened and so forth. And would they be useful for monitoring purposes? Because the more you have, the more detail you're going to be able to have on your basin, and the greater your ability is going to be to be able to base your decisions on observed conditions. You know, we all feel more comfortable about observations than, you know, this magic black box that's telling you what's going on out there. And then indeed, you know, the more of this type of information you have, the more confidence you're going to have in your model. But this is just a real important fundamental concept that carries over into modeling, because this is ultimately what a model is trying to solve. It's either trying to determine the flow, or it's trying to determine the water levels, or both, you know, depending on the problem that you're trying to solve.
Just a
Does
comment.
time become a factor in that any place?
Yes, yes.
How does that fit into the calculation?
Or at least to structure my talk around the steps of building a model. And in a lot of ways, it's kind of like building a house. I think that's a helpful way of thinking about it, in that, you know, the very first thing you have to do is, you know, is to develop that framework. You know, you have an idea of the house that you want to build, but you have to put up the frame, basically. And that is really based on, you know, your concept of what the groundwater system is like. And so you build up the frame, and then what we call that in model speak, you know, that's dealing with the mesh or the grid, and I'll talk more about what that is, but also dealing with what goes on at the boundaries, you know, of this house that you're building. Then the next step is that, you know, once you got your frame up, you know, you want to start putting in, you know, your pipes and your wires and so forth. So you're dealing with the electrical and the plumbing, and that's where we specify the properties of the aquifer, you know, the hydraulic conductivities, the ability of the sediment materials, the variability in the sediment materials, you know, that variability, what that variability means in terms of the variability in water transmitting and water storage properties of the materials. And then finally, or not finally, but then the next step is, you know, we begin to attach the exterior to the house, and that's, you know, what I think of as starting to develop like a lot of the water-related information, like the recharge, the water that replenishes the aquifer, the discharge, you know, the stuff that's coming out of the aquifer, you know, anything that would contribute to a balance, you know, the balancing of water inflows and outflows, like surface water flows that are coming in, or you know, in other areas of the state, imported water supplies, you know, recycled water programs, you know, land use, all these things start becoming really important in terms of determining, you know, the input that goes into the model and the movement of water. And that's kind of like putting up the exterior of your house. And then the fourth step is where you customize the house for your own purposes. And that's a lot like, you know, when you go in and you paint and you landscape it and so forth. Well, that's what I would call being analogous to calibration. And that's when you figure, you know, when you determine, okay, this is the house that I want to live in. This is matching what I want, you know, what I understand it to be. And then finally, you know, once you have it landscaped and painted, you move in, which is basically implementing the model, using it for the intended purpose that it was built. And so like I was saying, the very first thing to do is you construct the framework, and that's what you'll hear people talk about being the mesh or the grid. And, you know, in a very simple sense, it's more than simple, it's factual, is that you're taking this three-dimensional thing, this volume of sediments, and you're conceptually chopping it up into a bunch of little pieces. It's like all the little triangles that Rodney was talking about, okay? And you chop it up into a bunch of pieces, and then what you do is you solve that triangle problem that Rodney was talking about over all those pieces, okay? And so, you know, what I'm showing here is, you know, this is a picture or a map of the basin, and it's hard to see on here, but it's all chopped up into what's called a mesh. It's a finite element mesh. All you need to understand is it's a mesh, and it could be of varying sizes. And so when you're designing that mesh, you know, you can design it in a way that you know, provides you more information that you can use, you know, more effectively. And this is just an example of showing of how, you know, we have a boundary of an area here, which is one of the GSAs in the basin. And so you just design your mesh so that you follow those boundaries really carefully. So it makes it really easy when you want to sum up all the information that all these squares and triangles are giving you. If you want to sum up that information, you can do it really easily along those boundaries that are based on, you know, political you know, decisions and so forth. And so each of those little units, those little elements, those little triangles and squares, they're an area of the model where it represents things as being all uniform. So that's why there's a balance between, how big those mesh or those squares and triangles are, and how small they are. But within each one of them, all the stresses, meaning that the recharge, whatever the value is that we tell it, the pumping, whatever the value is that we tell it, the aquifer parameters, whatever values it is that we tell it, they're constant, but they can vary between each other. And so that's how you incorporate the complexity of the real world in it. Because one of the things we have to remember is that a model is just a representation of the real world, all right? And we can never do that precisely in terms of like complete accuracy. It's always an approximation. And so the art of modeling is determining, when that approximation is good enough for your purposes, or when that approximation needs to be improved. And so here's just a couple of, I've shown these to some of you before, but just to get your mind thinking about, the whole idea of a model and evaluating, how it's chopped up. And say, for example, that you had, this area here that you wanted to, for whatever reason, you wanted to understand or calculate what the area was underneath this shape, this curve, okay? And so you could go out there and you can approximate it by, I can calculate the area easily of a square or a rectangle, right? And so you can go out there and eyeball it and say, okay, this is about it. This area up here is making up for the area I'm losing here and so forth. And you can calculate it and get an approximation. But then you can also chop it up smaller. And you can see, I think intuitively, you begin to see that, yeah, there's still error. There's still areas of error that we're trying to compensate. But these three little rectangles probably does a better job of that one big rectangle. And then you can chop it up again. And so you begin to see, as you chop it up more and more and more, you begin to match that line closer and closer and closer. And that's the whole concept behind what they call discretization. You either discretize the model in space, which is the mesh sizes and so forth, or you discretize it in time. The distance, because all these things that I'm sharing with you in terms of spatially, they also apply temporally with time. You can be looking at how things change from year to year. You can be looking at how things change from month to month. You can look at how things change from day to day, from hour to hour, from second to second. Whatever it is, whatever the problem is that you're trying to solve. But there's always a tension there because the finer I chop something up, the longer it's going to take for the computer to do the calculations. And when I first started doing this stuff like 30 years ago, one of the real arts to it was to be the guy that can figure out, okay, I can solve this problem and still do it in a reasonable time with a computer, because computers were, they were slow, very slow relative to today. Now, unfortunately, they're relatively fast, memory's really cheap and accessible and so forth. And so sometimes you get people who, they get lazy, and so I'll just use a model and chop it all up. And you kind of lose something in that process of trying to, merge between the computer and the concepts that are in your mind. But this is an important concept to understand when you're evaluating a mesh or a grid. And this is the same idea, but I'm just doing it this time looking at a map view, where you can try to calculate the area with a single square. You start adding more squares and it's getting better, or now you start seeing what really looks like a model grid. You start chopping it up really fine, okay? So we chop up the model, in a map view, over the land surface, so to speak, but we also have to chop it up in the vertical direction. And sometimes you can just chop it up like you did in the map view. You just say, I'm just going to make what they call layers. I'm just going to make all my layers 10 feet, just however deep I want to go, and then I'll just pick off, what this layer represents, what this layer represents, and so forth. That's one way to do it. Another way to do it is you try to have your layers, like I'm showing here. The top and bottom of the layers are corresponding with other information, geologic information that we have, and this is one of those cross sections. And so you have differences in the formations, and so we can assume things vary with depth, but we'll assume that this formation behaves relatively similar, within itself. This formation behaves relatively similar within itself, but it could be drastically different between the two. So that'd be one other reason or that would be another approach to determining how to, chop your groundwater system up vertically. Then there are other considerations of like what we use, the term we use is like numerical considerations to make the computations and the calculations from the computer to make them easier on the computer, so there's a less likely chance of computer error. Okay, and so you can end up, even though this might be, based on geology, a similar formation, you can chop up the layers to be thinner just because you want to have, things might be changing rapidly with depth. Rapidly is probably not a good word, but they're changing with depth. Leave it that way. They're changing more with depth than maybe they're changing down in here. So that would be a reason to chop it up finer. In this situation, our decision to do that was because of the fact that the aquifer, the geologic formation is in hydraulic contact with the surface water, and so we want to do a good job of understanding what's going on with that interchange between water that's beneath the land surface and water that's in the river. And so we can chop it up finer to try to get more detail to look at things that are going on, relatively near the land surface. So that gives you a sense for, the mapping the structure. One of the interesting things I was going to talk now about conducting the frame is that we have this structure. Now we have to tell it what's going on at the boundaries of that structure. And that's something that's really easy to do. It's like a desert basin, like I was describing earlier, where it's just basically a valley surrounded by rock. That's really easy to do. But you have a situation like here where boundaries are rivers. Basin boundaries are rivers, and unfortunately, groundwater doesn't respect those boundaries, and it can move, beneath the river traces and so forth. So boundaries become a real important consideration in developing a model. And one of the things was, this is going to be a pretty long section in terms of just talking about boundaries, but the reason for it is because there is a lot of complexity here in this basin. You probably will use, if not all of those types of boundaries, at least three of the four. And so I thought it was important to kind of just give you a sense for what we're talking about, because this is the stuff that, these terms are things that are going to be talked about, fairly frequently in the future. The types of boundaries are no flow, specified flow, a specified head, or what's called a constant head boundary, or what's called a head-dependent flow, and I'm going to explain what those are. Okay. So the no flow is the easy one. Basically, that's like if you have an aquifer that is up against bedrock, water can't move, exchange between the two. So at this point in space, we just say there's no movement of water across that boundary. And so in that situation, if you had two basins, or you had like two basins, like say this is eastern San Joaquin and this is the Cosumnes, if there's a no flow boundary, what goes on in here doesn't affect what's going on over there. And that's not true here. But if that was the situation, that's the purpose of a no-flow boundary. So you don't even need to worry about this basin. All you need to worry about is this is your desert basin surrounded by a mountain. Okay? So that's a no-flow boundary. And here's an example of how it might apply here in this basin, where here is the concept where you have, this is your sediments that have water in it, your water-bearing materials and so forth, and they butt up against the underlying rock, and you approximate that contact as a no-flow boundary. And here's an example from an actual model grid that includes the Cosumnes Basin, where here's the boundaries of the basin, and where it butts up against the rock formations, you can represent that as a no-flow boundary. And what that means is that there's not water flowing into the basin through the subsurface, but that doesn't mean that water can't be flowing into the basin on the surface. Okay, it's not cutting off all water, it's just cutting off water that's moving beneath the land surface.
John,
Question?
are you implying there that just as an example, at the eastern edge, that might be the case, or is there data to suggest that actually is the case with the no-flow condition on the eastern edges of the sun?
Oh, I would say there is data to indicate that is the case just by the geology. Now, it's really important that this is a, this is a discussion in relative conditions, in that there most surely are fractures, say in a rock, that water can move. So it's not like there's a slurry wall there or a concrete wall. But in relative terms, it can be, when we're approximating what's going on, it can be ignored and called no flow.
So just so I'm sure I understand the implications of this, what you have up there suggests that there is little groundwater that is coming down into the Cosumnes Basin from the foothills. Am I correct in my interpretation?
And that is the reason why the basin boundary is placed there.
So is that based on geology?
Primarily, yeah.
And
Rock types.
a lot of us, have in our heads, and it's true, that we get a lot of recharge from the foothills. Well, it starts at the surface, probably near where that bedrock line is, and surface flow or snowpack are then infiltrating the shallower sands and gravels or rock cracks in the rocks, whatever, and getting into and the Merton Foundation, the Galt currently has just recently constructed a third deep well into. It daylights up above Jackson. I mean, that's recharging up above Jackson from surface waters. And then, by the time it gets here, it's 1,000 feet deep. And gravity is, and it might take 7 years for that drop of water that starts on the surface to get below Galt at this end of the aquifer.
So you're suggesting that bedrock then comes right up to the surface?
Well, you see that in mountains.
The Merton-
You see all that
Mountain,
granite.
but I don't see it up in the foothills. You see it sporadically in the foothills, some rock outcroppings and stuff, but it's not like in the Sierras where you see lots and lots of.
You can see a lot of scarps and things. I'm not a geologist, but I know from a lot of years of camping groups and up, you can get in an area in the forest and you got a lot of humus and moss and decomposed material.
Right.
But you go down to, let's say if you're with a Boy Scout group, you want to dig a tree, you get down about 2 feet, you hit a rock. So a lot of places, you may have soil covering the rock, but it's very thin.
I see.
And what they will do as part of the data gathering is define where is that rock and how deep is it? And that's that line that will progressively get deeper as you move into the valley. So for your 3D model, you do need to know where that rock is and how deep it is at any given point.
The one thing that may happen with that Merton formation, is if you want to see it, you can go to Kit Carson Pass where they cut the mountain out going around Red Lake. There's about a 2-foot strata that's showing there. But we don't know if that's the same Merton formation, or the same one that we have down here, or the one out past Slough House. Could they be different Merton formations at different levels in the land?
Yeah.
Right.
So you can see it at Slough House?
Yeah.
Oh, yeah.
Scott Road.
Scott Road.
Mice Road, you can see the bluffs on Mice Road. I got them all over my ranch.
And just so you don't get embarrassed like I did with an assumption, we call the aquifer we like to pull from the Merton Aquifer. Well, Merton is a type of soil. Okay, you can have Merton foundations all over the valley. It's a soil classification. In our case, there's a steady lens of it that starts very shallow and gets deeper. It's sediment layers that are very transmissible. So we just sort of call the aquifer, we're down in the Merton aquifer. Well, Merton is really the soil type that we're drilling into. The aquifer itself probably has different hydrogeological nomenclature. So just so you don't get upset, well, we're in the Merton aquifer. Well, no, we're not. We're in Merton soil.
Basically.
There is a Merton formation.
Yeah.
It sits under the lagoon formation.
Yeah, but you could also have that up
Sure.
near Lassen, you could have it down near Bakersfield. It's a soil layer.
it's just like we were talking about groundwater moving slow. You know, a lot of the topography is moving a lot slower. You know, like you go and look at what's going on just geologically along like the San Andreas Fault. You know, you can clearly see where things have been separating and shifting and so forth. So something that was down low, there could be uplift, you know, over eons, you know, that would lift it up into the, and you're seeing it up in the mountains. Yeah, at one time it might have been connected, but it's not anymore. So constant head, this is a boundary condition where what we're saying is that the water level is constant. It doesn't change over time, and I think, you know, one of the easiest concepts for that is just like thinking of if you had an aquifer in contact with the Pacific Ocean. I mean, we all know the tides go up and down, but over time, you know, it's basically staying about the same elevation, the average. And so it could be represented as a boundary where the water level is constant. And so what happens is that water level is maintained constant, and depending on what's going on in Basin A and what's going on in Basin B, it determines, you know, the water that comes out or in from that boundary. And I think, you know, maybe an analogy here would be like if these were like two basins that were, you know, like islands, you know, shallow island, you know, groundwater basins surrounded by the ocean, where, you know, what's going on in here is not going to really affect what's going on in here, but it is going to affect what's going on in terms of the movement of water between that boundary and what's going on in the aquifer. And in this basin, you know, something that might possibly be represented as a constant head boundary, a place where water level is constant, you know, it might be the reservoir. I mean, you know, we know water levels change with time, but in the long run, relative to what's going on around here, the movement of water either in or out of the reservoir is not going to change the level of the reservoir. And so you could, you know, legitimately say, okay, we know what the water level is with the reservoir. We can change that value like every month or whatever over time, but during that period of time that we're looking at, we assume that it doesn't change, that it stays the same. And I think, you know, that's probably a good example for the reservoir, in that, you know, the amount of groundwater that might exchange between the reservoir, say within a month, is not going to change the level of the reservoir. There are other things that are changing the level of the reservoir much more than that. And so that's an example where you might use like a constant head boundary in this basin. The other one that was on that list was specified flow, and all that means is that you know, the flow across the boundary, we have some kind of estimate of it, and so we tell the model what that flow is. You know, we may have you know, good water level data to tell us, you know, what that force is that is driving the flow. We may have good information on the hydraulic conductivity of the materials with depth and so forth, and so we can tell it what that flow is. And so the groundwater conditions in Basin A and in the groundwater conditions in Basin B are going to be influenced by that flow that we specify. Okay? Now, it's doubtful that we'll have that kind of information for this basin, but just for an example, remember this was that diagram I showed with the water levels, and you calculate the flow, you know, the flow going across this area of a you know, aquifer system. Well, if you had that data, you could specify that flow along the boundary of the subbasin. And that flow could be you know, either uniform, most likely not. That's why one of the reasons why we wouldn't be able to use a boundary condition like this unless we were doing something, just some simple calculations. But it can vary, you know, over from east to west, as well as from, you know, with depth. But this is, you know, where you would apply it along a boundary like that. Okay?
Well, John, I heard you say that we probably won't have the data to assess this,
Right.
but it seems like that's so important to understand it.
That's right. And that's why you have a head-dependent flow boundary. Thank you.
I was just sitting back to the next slide.
I know. And so what this boundary does is it says that say in groundwater in the Basin A, say we don't know what the water levels are in Basin A, but we know the water levels in Basin B. Say there's monitoring wells out there. And so what we do is the flow between the basins is determined by the water levels that we specify out here in Basin B and what goes on in Basin A, what the model calculates is going on in Basin A. And so what it's doing is it's determining or it's calculating the flow between the two relative to each other based on, on what's going on, what's being calculated within one part of the model and what's being specified as being constant for that period of time out externally to the model. And that's why it's called head-dependent flow. And so when you're talking about cross-boundary flows, that flow between the basin and the area outside the basin is going to be proportional to the water levels that you specify outside the basin and the water levels that are calculated inside the basin. And here's an example of where that might work. In this basin, and this can vary with depth, but just from looking at just from a map view, say you had wells out here that had water level measurements, some distance. They don't have to be the same distance, they can be variable distances, but you had something that you could hang your hat on. You knew the water level at certain points, and so you could estimate what that water, or you could have a contour map, say, of this area, or something that tells you what water levels are like out here. Then you could specify those values for this condition here along the model boundary, and then with the calculations that your model is doing, based on what's happening in here with your model, it'll determine the movement, not only the quantity, but also the direction across that boundary based on what goes on inside your basin and what you've specified is going on out here. Okay? So that's one of the ways that you get around with the fact if you can't specify the flux, you can have the model calculate it for you. But in this situation, you have to have those water levels. Okay?
And then that would be further complicated by any inflows from the Cosumnes itself at that particular boundary.
Right, and so that's why you may have different conditions in the shallow portions of your model or your groundwater system relative to what goes on at deeper depths. And speaking of,
So before you move on, so between the basin A and B, are you assuming with that chart that you showed the monitoring wells, they were both the same models?
no, these are wells. So these are wells we went out and measured.
Between the two basins, the boundary conditions, are you assuming that they're both constant on both sides?
No, the constant is assumed on the outside of, because we're modeling this.
Okay.
So the constant we specify is outside of our model. And then we're calculating what goes on in here with our model.
Okay. Thank you.
And associated with those water levels, we also are specifying, what that connectivity is between the two, which can vary, both east, west, and vertically.
Part of your data and that gap analysis will be, do we have appropriate monitoring well locations? Enough of them, are they at the right levels? Or is that going to be a need
Right.
to calibrate the models? We're going to have to drill some monitoring wells or work with the adjacent basin to have a joint project or something.
And in the very, in the strict sense, if we don't have the data, we do the best job we can at estimating it. And that may be a reason why you would use a specified flow boundary, because we don't have the data to do this. We can make some assumptions and try to specify the flow, but it's going to limit us, and that becomes something that you try to rectify or correct in the future.
Well, John, the fact that SCGA has done modeling for the basin would suggest that there must be wells there that we could use the data from to make those estimates. Is that correct?
It suggests that there's wells there and they may be useful. We haven't looked at what they tell us in terms of both their aerial distribution and the vertical distribution and their distances from us and so forth. But that'd be part of the evaluation.
How close do those monitoring wells have to be to the basin boundary?
Oh, that, I don't know. I mean, that's something you'd have to evaluate as part of the development process. You'd have to look at what you have. And you know, I guess the way I would answer your question is, if in this basin, in the shallow zone, I'd want them as close as possible. But in the deep zone, if they're farther away, that's okay.
So up to a mile?
For the shallow zone,
No, for the deep.
oh, it could be farther than a mile. It's all relative, you know, it's part of the analysis. You look at what you have, what can you do with it, and then you have to make a decision, okay, this is what I can do with it. I have to factor in the uncertainty or the sensitivity. That's part of the process of developing a model is just speaking theoretically here, you do the best job you can of representing this boundary. One of the steps is, well, how sensitive is this boundary to what I'm trying to achieve with the model? Okay, and it may turn out that wells a mile away are perfect. Or it may turn out that wells 5 miles away are perfect. Or it may turn out that I need to have in the shallow layer, I need to have wells within a half a mile.
So is it critical to pick one type of model versus another model? When you,
No. In that situation, it's more important of how you chop things up, so that you can make sure that you have, you know, if you need to consider wells that are within like a quarter mile of a boundary, you want to make sure that you have this thing chopped up enough to accommodate that, so things can vary on either side of where that well is.
okay, so the tighter the grid, the better.
If that's what you need. And in fact, that's one of the things we've talked about, is how when you're dealing with these boundaries where there's, you know, rivers, you want to have a tight grid.
Okay.
And when I was showing earlier, remember in the vertical, we chopped it up tighter? That's the reason, because along these boundaries, you want to have a tight grid in the shallowest part where that exchange is going on. As you get deeper, it's not as important.
So have a more complex model in the areas of sensitivity and use your money there. And then have sort of an economy of scale where it is less sensitive or less important.
Right. And this is, you know, important to this basin is, you know, the exchange of water between, you know, groundwater and surface water, and that's basically a special type of head-dependent boundary. You know, we talked about the head-dependent boundary earlier of the movement of groundwater, but here, you know, we're dealing with the movement of water that's in a channel, you know, surface water, and how that is exchanged with the underlying groundwater. And this is a special kind of head-dependent boundary where you can specify what that water level in the river is, or the stream, or the canal, or whatever it is you're interested in. And you can specify how that water level changes over time, you know, and depending on what you're modeling and what the objectives of your modeling, you know, you can change the water level from yearly to monthly to daily to hours to seconds to whatever it is that you're trying to, you know, relate to the problem that you're trying to solve. But you can specify that value as being the specified water level or the specified head, and then the groundwater model is going to calculate the movement of water between the two based on what happens in the aquifer. Okay, so it's just a special version of a head-dependent flow boundary, and that, you know, most definitely will be used in this basin. So finally, you know, some of the questions that you all were posing. You know, we were looking at the situation. Let me go back. We were looking at the situation where, you know, I'm building a model. This is the world that I'm modeling, and I don't want to know anything else that's going out here other than how it affects me. Okay. That's kind of what that was the basis of our conversation. And some of the questions you were raising was, well, you know, how far do these wells need to be? You know, what data do we need out here? How far away, and so forth. Well, a lot of those, you know, we don't know, or you don't have the information, and so you can't do this. And so that's what I call uncertain boundaries. There's some uncertainty. You know, we can make some assumptions. I mean, somebody could come in here just cold turkey and say, okay, well, this is a river. I'm going to assume that 50% of the water goes this way, and 50% of the water goes this way. And so this boundary, vertically, is a no-flow boundary. And we'll have water flowing, we'll specify half the flow going here and half the flow going there. Now I'm being, ludicrous, facetious here, but I'm just trying to, that's one way somebody would look at it, if they didn't know anything else. But what the reality is that a lot of times, especially in these kind of basins, where they've drawn the boundary of a basin based on something like a river and not on the physical boundaries of the aquifer system, you're going to have uncertain boundaries. And so this is some of the techniques that they use to deal with uncertain boundaries. And some of this stuff you've seen before. This is a map showing the model that was developed for the eastern San Joaquin. And one of the ways you deal with uncertainty in boundaries is that you build your model for an area that's bigger of your area of interest. And so this is where I want to focus, this is where I want to have really good output from my model. And I want to know what's going on with the boundaries. And so what I do is I can extend the model, in this situation we're extending it to the rivers. And I don't need the same level of detail in here. I just need enough in here that'll do a reasonable job of the model calculating what goes on across here. Okay? And so that's an example of where they'll build a model and they'll extend the boundaries farther away from the basin, when this is really the focus of your effort. Okay? So that's one approach to deal with uncertain boundaries. So if we don't know what's going on here, we don't have wells, enough wells, or we don't have wells a sufficient distance here, well, one of the things that you could do would be, you could, like they've done, is extend your model. And so, theoretically, we could do the same thing, extend it down here, if we decided to do that. Another technique is what we've talked about before, is either what's called linked or nested model. And what you're doing is you take the information from other models that represent much larger areas, and you take the information that model tells you at the boundaries of whatever your model is. It could be just the basin that you're interested in, or it could be an area of just the basin, including areas outside of it, like I showed you previously, where you model a bigger area than your area of interest. But what you do is you use this larger model. You take the output from that model, which is either the water levels that the model calculates, because it's going to give you water levels for the entire area here. So you can take the water levels that the model calculates for that boundary and for the depths, and you can specify them on a smaller model that you chop up really finely, and you put in more fine data that you've collected for your own purposes. But you use the larger model to specify the conditions along the edges of your model. And you can specify the flows. So we can specify water levels, or we can specify the flows that the model, the larger scale model is calculating in all the directions. Okay, and this was an example. This is actually an example of something that I did where we had a small area that we were interested in. We were looking at, this was really important to understand the direction of where water was moving and how it might be affected by pumping in deep aquifers beneath the shallow zone on either side of, this is South San Francisco Bay. And so what we had is we had this larger model that we used to calculate the groundwater elevations in these deeper aquifer zones as a result of the regional pumping that was going on. And then we would take those results, and here is this in the terms of contours, and we would just extract them and then apply them to our focused model. And so if you look really close, you can see that these are the same values here. And so then this little focus model, we have a lot more detail in there where like our layers are 25 feet thick, and the areas of the cell between, of the cell areas are really small, like 20 square feet or something, and a lot of variability in the geology and the water levels with depth and so forth. And we can analyze that real detailed information at this level, but we can incorporate what's going on along the bottom of the model by using this much larger model. And it would have been too cumbersome to develop that same level of detail for an area that's much larger. So there's an efficiency there. But this is what they call linked or nest models. And then finally, we talked a lot about the boundary conditions, and then the fact that we all recognize that we're trying to do an analysis in this basin, they're doing analysis to the north, analyses to the south, and they're using different models and so forth. And there's a need to make sure that, we're all saying basically the same thing. I mean, DWR requires that. But what does that mean? Consistency, across basin boundaries. Well, this is my opinion. One of the things is our model and their models or whatever they're using, that the direction of flow should be the same, right? I mean, if our model or our analysis is saying water's going this way, going to the south, and their analysis says it's going to the north, well, there's a problem there. We need to fix that. But if they're consistent in that regard, then there's agreement. The magnitude of flow, the total amount of flow that's going across boundaries from adjacent basins, it doesn't have to be exactly the same, but it has to be reasonably close. It can't be so different that one flow would lead you to have a different conclusion from the other. Okay, they have to be reasonably close, but they don't have to be exact. And then finally, this is important, is that the source of that flow or the sink for that flow, it has to be the same. You can't say that, maybe they're both saying water's going in the same direction. They both say it's the same amount of water's going in that direction, but one model can't say that it's all going in the shallowest depth intervals, and the other model can't say it's all going in the deep depth intervals. Okay, there has to be consistency there. And those are some of the, the things, the criteria that you would look at in terms of evaluating how your model is representing boundary flows and how it agrees or disagrees with other analyses that are going on around you.
So, John, on
Yes.
that point, how do you assess the flow how do you assess those factors? Is the flow direction the same, et cetera? It means, I guess, sitting down with the groups to the south and to the north and reviewing their analysis.
This could be very analogous to a situation like this where you build a model based on the data you have, but there were data limitations. And what I'm showing here is the change in storage decrease over time. But then as you got better data and you got better, more information, and you were able to improve the model and so forth, that result changed over time. And so it's just a matter of, or a process that it's not a new model, but in some ways it's just changing the way that you calculated an input because you've got some other related data. It just kind of diverged a little bit. In this example, one of the key pieces of information was like here, where there were areas that were large areas, turf areas that were using groundwater to irrigate the turf, and there was no meter for it, and so we were having to estimate what their pumping was. Well, they implemented a recycled water program for part of the basin, and one of the values of that recycled water program was that now they're starting to track the water that's being used on these turf areas. So we were able to evaluate how well our methodology for estimating the pumpage based on the recycled water delivery. So it had this indirect effect of giving us the ability to refine our methodology for calculating pumping from similar wells for similar turf areas in the basin. And that it had a huge effect because it helped us get a much better estimate of what groundwater use was actually, what it actually was. And so this is one of the beauties of this type of work, in that things start to play into each other. They start benefiting. There's cross-pollination that goes on.
An example for our region might be, we don't really have good data on how much water is used for drip irrigation for a various type of crop. But maybe some other area is going to implement a meter system, and Napa Valley that has lots of grapes, and we can start to compare climates and do some things. Is okay, well, they've done a study, maybe we can make some assumptions using their data. Okay, we're warmer, we're drier, we have more evapotranspiration or whatever, so we're gonna have to use more water. But we don't have to go out and install a meter everywhere. We might be able to calibrate our model using some studies that have been done by others.
So this is summarizing some of the things that we've already said, but in terms of model adaptability and maintenance, the level of effort in updating a model in the future really depends on the quality, not only now, the information we have now, but what we expect to have in the future. Okay, and then also it can change if if the question you're asking changes. For example, you may be looking at just a basin-wide water budget right now, but there may be a certain part of the basin that you want to have a better understanding of what the budget is in that part of the basin. That's going to affect, the level of effort in the future that you may want to put into, upgrading a model and then the way it evolves over time. Another point that I wanted to get across, which was we kind of were talking about a little bit previously, was the whole issue of model maintenance. Because the models are fairly adaptable. The issue of model maintenance, there's some principles, at least that I've observed, that make it a more efficient process. And one of them is, like I mentioned, consensus among the stakeholders. It's a heck of a lot easier to develop a model and use a model when everybody has confidence in it. It doesn't work when you have one group over here saying, oh, that's this and this, and complaining about this. And then you end up, in the extreme, you have competing models. You have different groups creating their own models. And that doesn't, that's not economically efficient. What's best is to go through a process where people agree upon what they know, and they agree on what they don't know, and they are comfortable with the level and accuracy of the information that they're getting with that information that they know. Also, the more you, the more people that have ownership of the model, as you maximize that, you get more people that feel like they have ownership of it. You have more people that are interested in maintaining it and updating it, and that's the most economic, approach. Is that it's not a burden that's carried by any one entity. It's carried by all the people that are interested in having a tool that does a good job. And you accomplish that by increasing the number of people that are relying on it, and you accomplish that by increasing the number of people that have invested in it. I'll just leave it at that. Okay, and then now this is the last section, and I think this can go pretty fast. And this gets to that whole thing of nomenclature, because we talk a lot about, you'll hear people talk about models and platforms and so forth. I wanted to just clarify that, when somebody asks the question, which model do we use? Well, there are different types of models. One of them, there are physical models, and this is a picture of a physical model of a groundwater system, and you can use that to solve groundwater problems. You can use that to solve problems just like a problem that you could use with a computer. There's different levels of accuracy. There's different levels of the type of information you can get out of it, but you can solve problems with it. And one of the great examples of it that I can think of is, I don't know if you've experienced it, but gone down to Sausalito. I don't even know if it's still there, but the Bay Delta model that's down there, it's a physical model. It's huge, and this huge airport hangar. And to be able to go there and watch them, this was like 25 years ago or so, but it was just so cool because they have all these little probes all over the place, and they're modeling the movement of salt water through these surface waters and bays and so forth, and it's a physical model. And they're doing the same thing that people now are using these really sophisticated computer models to do, but they did it with a physical model. I'm not advocating you do that for this basin, but it's a model. But then there's mathematical models, and that's what we're talking about. And within mathematical models, there are things that are analytical. It's where you can actually solve it. It's simple enough that you can solve the math to come up with an equation to solve your answer, to do your answer, or to come up with your answer. And an example of that would be, if you've heard of it in the groundwater industry, is like in an aquifer test using the Tice equation. They make some simplifications, and they're able to come up with essentially an analytical solution. And then there's numerical ones that basically are using the power of a computer to solve the equation. And the main point that I wanted to get across with this mathematical models is that when somebody says, or with the physical models even, when somebody says, which model should we use? Well, there's only one model. There's only one, and it's it's this three-dimensional partial differential equation of groundwater flow. This is the model, okay? And if you look close, you'll see that this is in three directions, but within these parentheses, that should look kind of familiar. That's the hydraulic conductivity, that's the difference in the water level, So there should be some familiarity there. And so what it's doing is it's calculating the changes spatially in water levels, and then over here is the change in the groundwater storage over time. Okay, so that's the model. But it's, it's a complicated equation, and you can't solve it analytically. So you have to come up with ways to solve it, either by simplifying things, by saying, oh, I'm only interested in groundwater flowing one direction, or some other kind of drastic simulation. If you're going to solve it in this form, you've got to use a computer. And so that's when the issue when people talk about platforms. There's not just one computer program to solve that three-dimensional equation, that model. And the most common platforms, and especially in Sigma, are these two. There's ModFlow, which is the USGS, and they came out with that. The first version of ModFlow came out in like 1986. And the USGS has been, supporting it, improving it, expanding on it ever since. They do a really, in my opinion, they do a really good job of supporting it and developing new tools and so forth that are free, that people can use. Then there's this model, which is it's a code of similar age, but it wasn't in this form, and it wasn't publicly available until fairly recently. But it's the integrated water flow model, and this is the one that DWR or Department of Water Resources is supporting. They're both free. They're both freely available, and they both meet all the requirements of Sigma. So if you were when you build your model, you're going to want to use either USGS, ModFlow, or you're going to want to use IWFM. And that doesn't mean you can't use something else, but those are the easiest ones because DWR is familiar with them and so forth. And they're doing the same thing, slightly different ways, but they're doing basically the same thing. They're solving that same equation.
Real quick question, nerdy, but has anybody independently looked at the correlation between the two models? Do they track? Do they produce very, very similar results?
Yeah, they do it by looking at them by comparing something that we know, like a simplified analytical model where we know the numbers exactly. They do it by comparing similar applications. There's all different kinds of ways that they tested it.
Generally accepted is that either model is fine.
Yeah, that's one of the reasons why DWR accepts either one. And there's a list of requirements. In fact, I have a slide for it later that what DWR is looking for in terms of what you do for a model. Now the applications, there are example applications of the model, which is the application is when your model is the equation, your platform is whatever computer code you use to solve that equation, then your application is the basin that you use that platform to create a model. And there are a number of existing applications that cover this basin. They all vary in the areas that they represent, but this is just a list. That there's the Central Valley Groundwater Surface Water Simulation Model. That's a model of the entire Central Valley. And I have a picture of that later that I can show you. And that uses the IWFM code. There's the Central Valley Hydrologic Model. That's a model of the exact same area, the entire Central Valley, but it uses ModFlow, the other platform. There's the Eastern San Joaquin Water Resources Model. That's the one we looked at earlier where it does include the Cosumnes Basin. The northern boundary is the Cosumnes River. And where they included it in the model, but it's not at the level of accuracy or detail that you're going to need for what you're doing, but it does cover your area. So one option you could be if you grab that model and you improve it, if that's what you wanted to do. I wouldn't recommend it for other reasons, but that's an option. It covers your area. There's the Sacramento Area Integrated Water Resource Model, and that's the one that it was called the SAC IWRM. It's actively being updated right now. And they're calling it this COSANA. That's the Cosumnes South American, North American model. And I have a picture of that here in a second that shows you the expanse of that, but it includes this subbasin. And then finally, there's this model, the Sacramento Valley Groundwater Surface Water Simulation Model. And the thing that's nice about that, it covers the Sacramento Valley, which includes this basin. But the nice thing about that model is that they developed it specifically to try to do a good job of understanding surface water, groundwater interactions, and primarily how that relates to groundwater and surface water transfers, which most of those are north of here. But that's what they did, and they developed it, and they were really looking at doing a good job of representing what goes on between the surface water, the groundwater. So it's something that can be considered. And any of these models, for your own unique purposes, you can reach into them and pull them out. Just like if you're building a car. You can take the carburetor from here, you can take this from there, you can take that from there, and you can put together your own hot rod. What do they call them? Rat cars or whatever? Rat rods, yeah. So I mean, there's all kinds of stuff that you can do with these applications. And this is just to give you a sense, a spatial sense. This is that Central Valley groundwater surface water simulation model. And here, if you can see it, this little pink area, that's the Cosumnes Basin. So this is the entire model. So that would give you a sense that, it's not going to be doing a real accurate job if you're looking at what's going on right here. But you could take this model and, here's your little sub-basin. You can improve it for this little area and then use that whole model to simulate what's going on across your boundary conditions.
John, I just wanted to get something clear. The difference between these applications relates to the numbers of layers, the size or the shapes of the grids. Anything else that differentiates?
Yeah, the level of detail in the input, how they distributed, aquifer parameters.
They wouldn't all use the same aquifer parameters?
No. I mean, like the Central Valley hydrologic model did a texture-based approach. That, like we were talking about the distribution of, that's how they distributed hydraulic connectivity. They didn't do that same approach for the C2V sim. Doesn't mean one's better than the other, because it really depends on what question you're trying to answer. But no, there is no consistency, like everybody did the exact same thing.
I don't understand what you just said. Could you clarify that a little? In terms of the texture-based approach, the aquifer parameters, seems like they would all be similar.
Well, what I was talking about, I spent some time earlier of that map from the San Joaquin Valley that showed distributions of sands and silts. So what you would, remember how I said you would have the high conductivities in the sands and the low conductivities in the clay? That's one way to distribute hydraulic connectivity over an entire model area.
And what would be another way?
Another way would just be,
well,
another way would be say, I have an aquifer test here, 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 and I'm just going to contour it. There's another way. Or you can say, I got all these aquifer tests, so I'm going to chop up my model, and then so that there's equidistance from all these aquifer tests, and within this chunk, it's one value. Within this chunk, it's another value. Those are all reasonable approaches. Or you can have just one value. I mean, this is theoretical, but so yeah, there's no, it all depends on how if you're just interested in determining like a volume of water, you don't need at the same level of detail in the distribution of hydraulic connectivity that you would need if you're interested in how, a VOC is being transported through the groundwater system. They're two different, but they're using models. Well, this is this is just to get the point across. Exact same area, but this is the Central Valley hydrologic model that the USGS developed, and so they based it on the texture, like we were talking about. Whereas the C2V sim, they're doing it a different way of extrapolating information across areas, different way of interpolating. Now, theoretically, if both models are giving you the exact same answer, and well, yeah, they're giving you the exact same answer, that in the extreme, that even though you might have these subtle differences at a low level of detail, when they're looked at in a larger sense, they're giving you the same answer. They're compensating for any differences. And so, you may, like, say, for example, well, I want to use the Central Valley model, that one of these existing models. You could take the C2V sim and you can take the CVHM and start going through this whole process. How do they distribute aquifer parameters? How does the model perform? Like we were talking about uncertainty. And you can say, well, this one, for us, this one works a lot better than this. Where if you were in a different basin, you may come up with the exact opposite answer. But in the extreme, they're coming up with basically this very similar results when they're interested in much larger areas, regions like Sacramento Valley versus the San Joaquin Valley versus Tulare Basin and so forth. And then finally, this is this is that that Cosumnes model that I was talking about, that they're actively updating, and one of the things that we're looking at. But here's the basin, and this is it doesn't show up very well, does it? It's much darker on my screen, but the boundaries of it are like this. And so it's including your basin, and it could be dealing with uncertainty in the boundary conditions by pushing them far away. So it's an option.
Does that go beyond the Bear River then? Is that what that is?
I can't. It doesn't go beyond that upper river, but yeah, that's Bear River. Yeah. But some of the attractive things about this is like I was mentioning earlier, you increase the number of stakeholders that want a reliable model, and you distribute it amongst a larger group of people and so forth. So there could be some benefits here, participating. And then finally, this is just a quick slide to just identify some of the things that like DWR is looking at in terms of sigma, and selecting a model and so forth. And like we talked about this, that whether you use whatever platform you use, it's got to be publicly available, has to be peer reviewed. Both of those has to be open to the public, and has to be able to get to the software. It has to be open and available to anybody. It has to make sure that it covers your entire basin. You can't just build a model for a portion of your basin. It has to do the entire thing. The boundary conditions need to be consistent between adjacent basin models. So like we were talking about earlier, if there was a significant difference between adjacent basin, that needs to be corrected. It's not going to happen overnight, but that's part of the whole thing with sigma. You put in your plan, and then you got 5 years, you got to give an update, and 5 years you got to give an update after that. And during that whole time, you're improving your ability to manage the basin. So you're going to have to correct those kind of issues. It has to be based on a detailed hydrogeological conceptual model, and that's what we were talking about in the very beginning. That diagram that showed the aquifers and where water was flowing in a basin and so forth. They have to do this sensitivity test and uncertainty analysis. And there, like you asked about like industry standards, there's a lot of a big range in what that means. And what I was saying was, I tend to focus more effort on this than you would typically see by others. Just for that very fact that I want to know how wrong it might be. It's great. It's not enough to say, oh, look how great this model is. It matches history so well. Well, that doesn't mean anything about predicting the future. And I want to know how wrong it might be in predicting the future. And then finally, the model adaptability. Does it have the things in it that can, deal with all the changes that might take place, like if you had to create a new project or something. And so I'm just going to finish up here with some of the takeaways from this lecture, I guess. Sorry to put you through this, and
we need it.
I very thank you for your patience. But basically, the key points were that to remember that the model and models are built to support you. They don't make the decisions for you. I mean, you have the ability to question the output from a model. Secondly, is to have your expectations aligned with the amount of resources that you have available and the limitations to represent the real world in this kind of way. No model is perfect. They all have a range of perfection, quote unquote, a range of accuracy, but none of them is perfect. In fact, the models are a representation of the real world system. So by definition, all models are wrong. They're all wrong. It's just we have to figure out how wrong they might be and whether we can live with that level of error. The models can be updated and improved over time, and that's determined by the quantity and quality of not only the data that you have when you build it originally, but how you improve that over time into the future. And they also can be improved and updated as the questions that you have to answer change over time, if they do. And then finally, the maintenance and the improvement of a model, that effort, it's most efficient when you maximize those entities that have ownership of it and have bought into it rely on it for using it for whatever purpose they may have. And so that means you got to develop, put the time in to develop consensus among the different stakeholders, to identify, what you agree on and where the uncertainties are and the limitations and the strength and so forth. And then ultimately, having a large base of owners, it also helps distribute that cost over a larger area. So it's not just one single entity that's footing the whole bill. So, yeah, so that's it. I guess I can answer more questions.
Any final questions for John?
John, I don't think you wasted our time. We needed this information.
Okay.
Thank you very much.
Thank you all for coming.